Well, hello, chemistry students. Here we are. We're now going to jump into chapter 18 together, which is a discussion of organic chemistry. Now, organic chemistry is well known to many college students as being one of those subjects that is a weed-out class, especially if you're interested as being a chemistry major or a chemical engineering major. Organic chemistry is exceedingly important to those studies and is notoriously difficult. We're going to only look at the first two sections of this chapter. We're getting towards the end of the year, and I wanted to give you at least a little taste of both organic chemistry as well as a little bit of material science and then a little bit of nuclear chemistry. So the only way I can get at that is by just giving you a sampling of each of these chapters and not require every element of it. As you look through this chapter, you'll probably be really glad that that's the case, that we're only going to be looking at the first two sections, because there's probably enough there to give you a taste for what is to come should you do further studies in the realm of chemistry. And if you don't, at least I'm giving you a flavor of it by looking at it in general, and then we're going to talk a little bit about hydrocarbons, which seems particularly appropriate for us living as we do here in Houston. You should have some familiarity with hydrocarbons. So we're going to get into this together. So we'll be talking in section A about organic compounds in general. So organic compounds are covalently bonded carbon compounds. So carbon is the key factor to organic chemistry. There are some exceptions, though, to that. Carbonates and carbon dioxide and carbides would not be grouped under organic chemistry. But otherwise, in general, if carbon is present in the molecule, we're talking about organic chemistry. This is because the carbon atom is somewhat unusual. There are many more times carbon compounds as there are all other compounds. So compounds containing carbon, there are more of those compounds than there are all other compounds. The question here is why? Well, carbon is unique because it forms, remember, 4 bonds are available with every carbon atom. Remember when we looked and did electron dots diagrams for carbon, you remember that as we would do that, we would see that as it relates to valence electrons, carbon has 4 electrons that all could be paired with something else, thus forming up to 4 bonds. And because of its electron affinity, it creates a lot of covalent bonds, and it bonds to many different atoms, including other carbon atoms. So carbon likes to bond with other carbons, but it also likes to bond with other atoms, which makes it uniquely able to form very complex molecules, as you will see. So in organic chemistry, structural formulas become very, very important in order to describe organic molecules that we're looking at. As just one example, C2H6O could be either ethyl alcohol or dimethyl ether. And these look like this. Note in both of these, we have exactly 2 carbons. Notice 2 carbons both ways. And then if you count the hydrogens, you got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have 6 hydrogens involved. And then notice you have 1 oxygen, 1 oxygen. So we have the same number here. It's C2H6O. But the structural formula becomes so helpful, indispensable, because the structure of this molecule changes a lot of its properties. And so in organic chemistry, it's not just the molecular formula, or not just the empirical and not just the molecular formula that's important, but the very structural formula, how these things are put together. Just to kind of show you that again, here's ethanol and here's dimethyl ether. You notice here the same molecular formula, C2H6O, but note the difference. Here's the space-filling model here, but here's the ball and stick models. And you see that they look very different and they behave differently. Organic chemistry nowadays almost drives me mad, said Friedrich Wöhler. To me, it appears like a primeval forest full of the most remarkable things, a dreadful, endless jungle into which one dare not enter, for there seems to be no way out. What he's commenting on is the tremendously expanding field that is organic chemistry. There is more expansion in organic chemistry than there is in any other field of chemistry. So if you're interested in chemistry at all, this is definitely an expanding field where new products are being developed every day. Continued research continues to happen. More and better products are happening as a result of the work of organic chemists. So we're going to talk a little bit about hydrocarbons. Hydrocarbons, you can kind of guess from this word, hydrocarbons, have only hydrogen and carbon atoms. They are the simplest of the organic molecules. So we're going to be spending our time talking about hydrocarbons, and they are the simplest of the organic molecules. What you would see in further sections in this chapter are substituted hydrocarbons, where you have another element that's also being substituted in the place of hydrogen atoms, and then all kinds of other arrangements that can also take place. But for our purposes, for this class, we're just going to deal with the first two sections, and we're going to talk about hydrocarbons, which are the simplest of molecules. So hydrocarbons, the simplest of the organic molecules. So here we go. Let's talk about them a little bit. So there are two main groups of hydrocarbons. There are aliphatic hydrocarbons, and there are aromatic hydrocarbons. The difference is the aliphatics are, they're either straight chains or they're ringed together where the end of one gets attached to the other side. The aromatic hydrocarbons have a particular ring, these rings with these loose electrons. And so we're going to be looking at the aliphatic hydrocarbons together. We won't even be really dealing with the aromatic ones in our class because of our time purposes. So let's talk about aliphatics. They can, in their simplest forms, they're just single bonds between the carbon atoms, and these are then called alkanes. So A-N-E, if all of the bonds between the carbon atoms are single bonds. But if we have a double bond in there, even one double bond, then it turns into an alkene. Note we have the E instead of the A. And this just denotes that there is at least one double bond in the molecule. If we get to a triple bond situation, we call that an alkyne. Notice here now we have the Y instead. So we go from A to E to Y. Alkane, alkene, alkyne. And alkyne tells us that there's at least one triple bond in the molecule. Now they can also be, as I said, sometimes these chains can also be looped together and connected into a ring. Cyclobutane is an example. This would be butane if it went from this carbon to this one without this connection. But if there's a connection all the way around, then we just add this word, this prefix in front of it, cyclo, to just tell us that it's cyclobutane. Remember, it's an A here because they're all single bonds. Here we have cyclohexene. And again, the E is there because there's at least one double bond present in this molecule. But cyclohexene is, again, this hex tells us that there are 6 carbon atoms. Here the bute tells us that there are 4 carbon atoms. We'll look at a chart in just a moment. But just to give you an idea of how the aliphatic rings go, they just attach from one end to the other. And then we use cyclo as a prefix to say that it's actually existing as a ring. Now the aromatics have a special ring structures with loose delocalized bonds, and we're not going to be dealing with those very much here because of our time constraints again. So which aliphatic has at least one double bond between carbon atoms? At least one double bond. So is it alkene, alkyne, or alkyne? Remember, it's alkene. The E here is the letter we use to describe double bonds, right? So the doubles are with alkenes. So here's kind of an overall organizational chart for this. With organic compounds, if they're delocalized electrons with the benzene ring, those are called aromatics. We're not going to be dealing with those here together. If it doesn't have a benzene ring, then they're called aliphatics. And the aliphatics then split into alkanes, alkenes, and alkynes. And any one of these can be straight or cyclic. If they're cyclic, if they're a ring, we use that prefix cyclo in front of whatever it is that we're looking at. Okay, so let's start with the alkanes. So these all have single bonds between the carbon. They're called saturated because they have the most amount of hydrogen that is possible. Whenever you change from a single bonded situation, with a single bond, you've got, remember, each carbon has 4 bonding sites. So if it's bonded to another carbon, each one of these other bond sites can hold a hydrogen. So each one of these holds a hydrogen, all 6 of these would. But the moment that instead I go to a double bonded carbon, remember, carbon has 4 bonds to give, but if it's 2 are shared here, it only has 2 left. And that means now there's only 4 hydrogens that could be attached to this. Whereas this molecule up here had 6. This one only now can hold 4. So when we use this word saturated, we're saying that there's the most possible amount of hydrogen that's been attached to it. And alkanes, by their nature of being all single bonds between the carbons, means it gives maximum sites for hydrogen to be attached to it. So those are called saturated hydrocarbons if they're all single bonds, which is what an alkane is. So alkane aliphatics are molecules that have a maximum number of hydrogen atoms attached to them. So a lot of fuels, gas and gasoline, are alkanes. They are nonpolar. They have no positive or negative ends to them. They are separated by fractional distillation, which is something that is happening here in Houston for sure. You can see distillation towers around, especially down the ship channel area. And longer ones are waxy solids. Now, before I go any further, I want to make sure that you are familiar with the numerical prefixes. I already started to talk about them a moment ago when we saw cyclobutane, and then we looked at cyclohexene. So in those cases, but stands for 4, hex stands for 6. But let's look through each of these. So 1 is, we use the prefix meth. 2 is eth. 3 is prop. 4 is but. 5 is pent. 6 is hex. 7 is hept. 8 is oct. 9 is non. And 10 is dec. So these are the prefixes we're going to be using to describe the number of carbon atoms that are present, whether it's an alkane or an alkene or an alkyne. So whether it has all single bonds, or if there's at least one double bond, or if there's at least one triple bond, that's what changes it from ane, ene, or eine. But we're going to be always using these prefixes for the number of carbon atoms that are present. So it's either, if there's only 1 carbon, it's going to be meth. If there's 2 of them, it'll be eth. If there's 8 of them, it'll be oct. And you'll see it in the examples to follow. So with alkanes, we'll start with the very first one. Here's just 1 carbon atom. Remember, it has 4 bonds. So each of these bonds are then connected to a hydrogen. An alkane, by its very nature, that's all that you can do with 1 carbon because it can't be attached to another carbon. So this is called methane. Remember, we use the ane because it's single bonds of carbon, and we use the prefix meth for this. So methane is 1 carbon with 4 hydrogens. So CH4 is methane. Also referred to sometimes as swamp gas. This is the gas that's given off by decaying substances, methane. If we get to 2 carbons, this is ethane. We use, again, that prefix eth for 2, and then we use ane because it's a single bond right here. So there's 2 carbons, alkane, that's called an ethane. If we go up to 3, we call it propane. Propane. Remember, we use prop for 3 carbon atoms, all attached with single bonds. So we use the ane ending here, and we use prop as the prefix because that's what 3. So 3 carbon alkane used for heating, propane. Some of you might have propane tanks at your house if you're living a little more out in the country. Then we get to 4. 4, we use the prefix but, and that becomes butane. And again, this is found often in lighters. Butane, it's 4 carbons, but then again, all hydrogen atoms attached to all other bonding sites. Once we get up to 5, we have pentane. Same principle. Once we get to 6, it's hexane. Do you see the pattern now? Can you guess what 7 is? 7 is heptane. 8 of them, octane. 8 C's. And this is a reference against which other fuels are compared in gasoline. So if you go and get gasoline for a car, you'll normally see that it's referenced to its octane level. So it's just a reference against which other fuels are compared in gasoline. Octane has 8 carbon atoms, all single bonds throughout the entire molecule. You see how these just get longer and longer. So 9 would be nonane. Nonane. And 10 becomes decane. So there's 10 carbon atoms all joined to hydrogen. So notice these can get very, very long chains. And organic chemistry, you might have some base like this. And what you'll find out as you get further and further into organic chemistry is you start substituting out certain hydrogens here and substituting in for that in its place. other systems of molecules, and you start to manipulate this molecule and creating different organic molecules from it. Okay, so which alkane has 7 carbons in its longest chain? So if it has 7 carbons, we're looking for the prefix hept, right? So we're going to say heptane. Okay, now we're going to now consider for a moment the old groups. Example here, methane to methyl. So methane, as we already learned, is just 1 carbon filled around with hydrogen atoms. But if instead we take a methane group and we want to join it to another existing chain. So let's say in this case, we've got butane that's here. We've got 4 carbons. And usually, right in the place of where this carbon is, we would normally have a hydrogen atom. But instead of that, we've taken like a methane molecule and we've joined it on here. Except in order to do that, we had to lose 1 hydrogen, right? And so we're left with this C with 3 H's around it. When we do that, this group here is now called no longer methane, but methyl. We call this a methyl group. So CH3 attached to another alkane here, it's called a methyl group. So CH3 attached to a chain like this is called a methyl. Now, an isomer is a substance with the same molecular formulas, but with different structural formulas. Like the example that we used earlier here in the lecture, ethyl alcohol and dimethyl ether both have the same molecular formula, but they have different structural formulas. They're combined together in a different structure. So there's some rules for naming isomers. So first of all, we find the longest continuous chain, and we call that the parent chain. Then we number the carbon atoms of the parent. Thirdly, we start at the end of the parent chain, which gives the lowest numbers, and name the side chains, the ol groups from that side. We then use a prefix if the same side chain occurs more than once. And we arrange the side chains alphabetically, ignoring numerical prefixes such as di, tri, and tetra. I'm going to give examples for all this in a moment. So note in the following slides, the H's have been omitted for the sake of space. So for example, this would normally be what we're looking at when we're talking about propane. But instead, we're going to write it this way. And you're going to just assume that wherever there's a carbon atom, if there isn't anything listed there, you can assume that what should be there are the H's, okay? So we're just going to make it easier on ourselves by just assuming that those H's are there, but we're not just having to rewrite them over and over and over again. This becomes really important in organic chemistry, otherwise you would just die of writer's cramp. Because you can imagine if you were working with these all day and having to write all those H's, which everyone just assumes they are hydrogens unless you say otherwise, okay? So that's how this works. So we can just talk about the chain and just assume that the hydrogens are there. So for example, let's look at this one. We have a carbon chain where we've got 1, 2, 3, 4, 5, 6, 7 carbons. But if we're trying to look for a longest chain, if we started here and went this way, we'd only have 5, notice. But if we start here, go down, and then move this way, we would have 1, 2, 3, 4, 5, 6. If we went down this way, we'd only have 4. So remember the rule is we find the longest chain. So in this case, it would be this chain that is the longest chain. So the longest chain, see, if it was that one, that's not right. It's going to be this one that is the longest chain. Then we number the parent chain, starting with the end closest to the side group. So notice, if this is the chain, this is now the side group. And we just have to determine which side is closer to this. Is this side closer, or is this side closer? And it becomes evident that this side is closer. So we start naming these carbons from this side. 1, 2, 3, 4, 5, 6. We then name what this base is. Remember, there are 6 carbon atoms here in the parent chain. Thus, it is hexane. We label it as hexane. Step 4 is we add the side chain name to the parent chain name. So we have the side chain. Remember, we learned that C by itself like this, you remember this would really look like this, C with 3 H's on the other sides of it. That's a methyl group. So we would call this methyl, and we keep this hexane. So we just write it methyl hexane. Those are the 2 parts together. You remember we got hex from the 6 carbons that are here, and then the ane because they're all single bonds. So we have hexane for this. We added a methyl group, and so that's why we say methyl hexane. And then lastly, we have to indicate the position of that side chain. And because we started counting from the side that's closest to the side chain, we count carbons, 1, 2, 3. It's attached to the 3rd carbon, so we would call it 3-methylhexane. And that's how we'd name that one. Okay, let's look at another example. So again, we need to first of all find the longest chain. So let's try to count these out. So let's start over here. 1, 2, 3, that would be longest. 1, 2, 3, 4, 5, 6, 7, going down that way. But notice I've got other stuff over here with additional chains out. So in this case, it's probably going to just be this guy is going to be our parent chain. Okay? So we find this longest chain. Now, we identify how many carbons are present in this longest chain. So we count them out, 1, 2, 3, 4, 5, 6, 7. And what's the prefix for 7? It's going to be hept, right? And then, we'll come up in just a moment. And then we can count these carbons. And what we're doing here is we're counting them here this way because this group is closer to this side. We have more activity on this side of the molecule. So we're going to start our counting from the side that includes this double, this ethyl group. So we label the parent chain as heptane because we have 7 carbons that we counted. That means hept, and we use ane because they're all single bonds. And then we identify these side groups. So we've got a methyl group there, and I just told you an ethyl group here. How did I get ethyl? Well, remember, ethane would be this arrangement. These are all hydrogens on here. So if we just break it down to just the CC, that's the ethane. But if it's attached to a side group like this, we change it from ane to just ul, the YL ending. So we call that ethyl, just as we call this methyl. So we have methyl and ethyl. We then label these side chains alphabetically. So does E or M come first? Is ethyl or methyl earlier in the alphabetical order? Well, ethyl comes first. So it's ethyl, and then we have 2 methyl groups, right? We have ethyl and methyl-methyl. So we can write that. Ethyl, comma, methyl, comma, methyl, heptane. Ethyl, methyl, methyl, heptane. That's how we would say this. Now, we note the last step here is to use prefixes for our side chains that occur more than once. Notice we have methyl twice. So we're now going to use the prefix di to bring that together. And this becomes then ethyl dimethyl heptane. Ethyl dimethyl heptane. And now this last step is we need to tell where these groups are located. And we do that from the numbering that we already did. So the ethyl, remember here, by the way, I said on the previous instruction as well, we leave it ethyl because ethyl comes before methyl. We don't allow the di to then make this come before it. It's not based on this prefix, it's based on these ones. So ethyl is before methyl because E is before M. So we write ethyl first, then methyl. And we have dimethyl because we have 2 of these groups. So for the ethyl group, we count how many C's over. It's the number 3. So it's 3 ethyl. And then we count the methyls. We've got 1 at 2 and we've got 1 at 6. So we'll say 2, 6. Which should look like this. As we label these side positions, it's 3 ethyl, which is here. 2,6-dimethyl, that's here and here. Heptane, because there's 7 carbons in the big chain, and they're all single bonds, so we use ane there. So 3-ethyl, 2,6-dimethyl heptane. Now that's a mouthful. That's a lot. Let's do another example. So again, we start off by identifying the longest chain, and here it's just the 5 right down the middle again. Then we number the parent chain starting with the end closest to the side group. Now you might argue you go either way, but this has, again, more activity on this end than on that one. So we're going to start our counting from that side. 1, 2, 3, 4, 5. Then we're going to label the parent chain. And we're going to note here that it is pentane. There's 5 carbons in this molecule. So pent, remember, is the prefix for 5. And you can review those in that chart if need be. Then you label the side chains alphabetically. In this case, note that they're all just single carbons that are attached. So those are all methyls. So it's just like methyl, 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 right? So we can though use a prefix instead of saying methyl, methyl, methyl. Use that there's how many of them? There's 3 of them. So we're going to use the prefix tri to say trimethyl pentane. And now we just have to identify where those are located. So we've got 2 of them attached to the second carbon and 1 of them attached to the 4th carbon. So what we do have to indicate both of them. So we have to say 2, 4. And that tells you where they are. So there's 1 at 2 and another 1 at 2. So we say 2, 2, 4, trimethyl pentane. Okay, name this molecule. Now this is a little tricky on purpose, right? So if I was counting this, the longest chain, 1, 2, 3, 4, 5, 6, 7, 8. Now, is this a methyl group? Is this one methyl octane, as this is saying? Or do you just keep counting? And that's the answer. You just keep counting. So in this case, if I wrote the C's like this, and then had it come this way, 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 and stopped, you just count it wherever it goes. So 1, 2, 3, 4, 5, 6, 7, right? So here it's 1, 2, 3, 4, 5, 6, 7, 8, 9. This is not a methyl group. This is just the continuance of the same chain. So there's 9 of them. So we're looking for the prefix that means 9. Oct means 8. Non means 9. And they're all single bonds. So it should be number 3, nonane. How about this one? Now notice here as we count again, 1, 2, 3, 4, 5, 6, 7, or 7. Either way, we get the same number. But remember, we want to count from the side that's closest to this chain, this off group. So we start from this side, going 1, 2, 3, all the way up 4, 5, 6 to 7 here, right? So we know we have 7 of them. And so we know it's going to be heptane, which happens to be the answer in each and every one of these. Then we just have to look at this guy. Is this just 1 carbon or 2? If it was 2, it would be ethyl, but it's not 2. It's just 1 of them, so it's going to be a methyl group. And now the last thing we just have to ask is, where is it located? Remember, we start our numbering with the side closest to the offshoot group. So this should be the second carbon. We start from this side, number 1. So that means it's closest to this side, so it's actually 2. So we're looking at this answer. It should be number 2, 2-methyl heptane. How about this molecule? Oh, this is fun, isn't it? So again, we're just count the longest chain. And again, I think this one's kind of self-explanatory. It's just this guy right here down the middle. So we're going to start from the side that has the most stuff going on, which is here, the closest stuff to the end. So we're going to start here with 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 carbons, which we know we use the prefix non, right? And they're all singles, so we're going to say ane, non-ane. That's going to be our molecule. But now we have to just identify where these are. Remember, this would be 1, so that makes this 2, this carbon 3, this carbon 4. So now we're just looking for something that has 2, 3, 3, 4. 2, 3, 3, 4. And notice here, tetra, because there's 4 of these methyl groups, methyl nonane. So this will be number 4. Are you getting the hang of this? Hope so. If not, so you can rewind and watch this again and maybe become more sensible, or you can read the book a little bit further, or you can even reach out to me if you're still struggling. Okay, now when we get to the alkenes, we're now talking about at least 1 double bond existing within the molecule. More bonds between carbon and less hydrogen bonded. That means that these are unsaturated. So remember, it's only saturated if it's an alkane because it has maximum amounts of hydrogen. The moment you introduce a double bond or a triple bond, if it's an alkene or an alkyne, it's no longer a saturated molecule because it has less hydrogen attached to it because some of those bonds are being taken up by additional bonds between the carbon atoms, which are now not available for hydrogen to be bonded. So in this case, these 3 carbon atoms are all single bonded, so it's saturated. But in this case, we have a double bond, it's unsaturated. Note that there are 2 less hydrogen atoms here than this one. So So this is unsaturated, whereas this is saturated. This is an alkene, whereas this is an alkane. So examples of alkenes structural formula: ethene there is just with a double bond, and notice that there's no other choice for where this could be. It's just ethene. Propanone, it's going to be propanone if it's there, or if it was written like this, it would still be propanone. And the reason why is you count again from the side that's closest to this. You could flip this molecule around, you could twist it around, and depending on where you counted from, it's always going to be in the first position. So note here, this would be propanone. With bute, you have butanone, or you could have butene, because in this case now it's in the middle of the molecule. So what you're doing with this 1 or 2 is you're locating the number of bonds it is away from the end of the molecule. And you always start from the side closest to the double bond. Okay, so alkenes are large alkenes with double bonds in more than one place, pent-1-ene or pent-2-ene. 2 double bonds, so we then say diene. So if it has 2 double bonds, we would say diene. If it has 3 double bonds, we'd say triene, and etc. On and on it goes. So here's an example of working a problem. So let's try to identify what this molecule is. First of all, we find the longest chain, which is just right here. And we're going to start numbering. Note this, whenever you have a double bond involved, we now start numbering from the side closest to the double bond. So in this case, that's this side. So here's bonds: 1, 2, 3, 4, 5, 6, 7. Notice there's 7 bonds, but there are how many carbons? 1, 2, 3, 4, 5, 6, 7, 8 carbons. So we number then the parent chain: 1, 2, 3, 4, 5, 6, 7, 8. With the side starting with the end closest to the double bond. This is an exception to what you just learned with alkanes. With alkanes, you would have started numbering from this side because of this methyl group. But the moment you introduce a double bond, we now start counting with the side closest to the double bond. If this double bond was over here, we would have started counting over here. But it's over on this side, so we have to start counting our carbons even from this side. We count the bonds from this side, looking at the bonds down below there. But we also then start counting the carbons from this side. Okay, so don't mix that up. Whenever you introduce a double bond or a triple bond, you start all the counting with the side closest to the double or triple bond. So in this case, we have 8 carbons, so it's octene. Remember, we're using ene here because that indicates there's at least 1 double bond in the molecule. We label the side chains alphabetically. We only have 1 side chain. It's this C by itself. Remember what we call that? If it was C by itself, normally it would be methane, but because it's a side group, we call it methyl. So that's a methyl group. So methyloctene. And now we just have to identify where these things are located. So the methyl group here is attached to the 7th carbon as we have listed here. So it should be 7-methyloctene. And then we identify which bond has the double bond, and we count the bonds. 1, 2, 3. And so we say 7-methyl, because that's where the methyl group is, oct dash 3, because that's indicating where the double bond is, ene. Remember, if there happen to be 2 bonds, 2 double bonds, like this or something, then we'd have to say diene. We'd insert di here, and we also say 2, 3 diene. Okay, that's how you would change that if there were more double bonds in the molecule than just 1. So name this molecule. Again, we're going to count carbons. 1, 2, 3, 4, 5, 6, 7, or you can go 7 here. Either way, you get the exact same number. So it's going to be heptene. Again, we have that in each of these examples, hept. But then we notice here that this double bond is actually in the very first position, the very first bond. So it's already going to give away that it's 1-ene. And then we know that we count from this side, the side closest to the double bond for carbons also. So 1, 2, 3, 4, 5, 6. So 6-methyl hept 1-ene is the answer to this problem. Okay, and then when it comes to alkynes, you follow the same principle. Remember, this Y now indicates that we're dealing with at least 1 triple bond between carbon atoms. These are also unsaturated just like the alkenes because, again, there's additional bonds between the carbon atoms, so there's less hydrogen that could be attached to the molecule. These are very reactive. Naming is the same as alkenes, except we change from ene to ine. We went from ane to ene to ine. It's the same principle. So here, instead of ethane, we have ethyne. Or instead of ethene, we have ethyne. It becomes then propyne, because there's a triple bond there, but1-ine, or but2-ine. Remember, if this triple bond happened to be over here and not here, it would still be but1-ine, because we count then from the side that's closest to wherever it is. So it'd still be but1-ine. But when it's in the middle, it has to be but2-ine, because if I count from here, it's 1, 2, or if I count from here, it's 1, 2. So either way, it's but2-ine. And here, pent1-ine, here we're just locating where that triple bond is. Here's pent2-ine, because it's in the second position. And then once we get to hexine, we can have it here in the first position, we can have it here in the second position, or we can have it here in the third position. Okay, so that's actually my last slide today, because I'm only dealing with the hydrocarbons and not any of the substituted ones. If you're just curious and you just want to learn more about organic chemistry, which is awesome if that's you, you can go ahead and look into sections C and D and E, and you can learn a little bit more about organic chemistry, about various substituted hydrocarbons, how alcohols are formed, how ketones are made, even gets into aminodes and amines and all kinds of stuff. So you can look into some of those if you want. I'm not going to hold you responsible for those on the test that is coming. But if you're curious, you can look at it a little bit more in the chapter. We're just going to be doing sections A and B for the purposes of testing. And if you guys have any questions on any of this, please do let me know. I'd love to help you any further that I can, or just watch through this video again. Maybe it will become more clear. Read the chapter itself, but hopefully I was able to kind of walk you through this. But let me know if I can help you any further. Love you guys. Hope you guys are staying safe. Look forward to seeing you again. I don't know if we'll be able to, I don't know how things are going, if it's going to be like this for the rest of the year or not. It kind of seems like it might be the case. But anyway, I'm praying for you. Let me know if there's anything I can pray for you specifically about. But God bless you guys, and I'll talk to you soon. See you next week. Bye-bye.